What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
Well, I'm at the next step now of building up this service yard for the Lehigh Valley Terminal Railroad. And the next step, of course, is the turntable. It's a turntable kit that I purchased. Is the Walters, see if I can show it to you, there we go. It's the Walters 90-foot turntable, non-motorized. And along with that kit, I purchased the motorizing kit. Is this little guy right here. And what I started out doing was I took the kit, I figured I'd check the motor and make sure that it was working and just see how it works too. And when I hooked it up to the power supply that I'm using to supply voltage, the motor didn't work. And it was vibrating, but nothing turned. So I decided that it's probably just binding. So I took the cover off of it. And sure enough, when I had the cover off and I applied a voltage to it, the motor started turning. So I put the cover back on again, but I didn't tighten it. It was, when I took those screws out, I had to get a relatively large screwdriver to back them out. They were really tight. And I think that's what happened, was the case was jamming the gear and a supposition. But anyway, while the lid was off, the motor did work. It worked fine. So I put the lid back on, but I didn't tighten it down, the way they had it. And this now works, and I'll show you. I'll apply some voltage to it. This is going to be that's about 5 volts right there. How do I know? I measured the voltage, that's how I know. So, if you listen carefully, you can hear it humming. And, it's not terribly loud, but it does make a little bit of noise. And it actually goes away if you dampen it. That's pretty nice. But that was an important step. I had to know that at least that the motor worked, and that I would go and build this kit. One of the things that I also need to know, and I'll share with you right now, is that I bought this encoder. This is an incremental encoder, not a positional encoder. There are 2 types of encoders, if you weren't aware of that. And an incremental encoder, it gives you pulses with positions as it's going around. Like it starts going in a direction, it'll give you some pulses, and it gives you 2 pulses, 2 separate pulses, and they're slightly out of phase. And for that, it's called quadrature. And what that is telling you, the 2 out of phase are telling you the direction that it's rotating. So when one leads the other, it's in one direction. When that same one's lagging, it's in the other direction. So that's the incremental encoder. The positional encoders are really expensive. And this particular one was surprisingly inexpensive. I'll put a link to the Amazon location where I purchased it in the description of the video, so you can see that. But the next thing I want to do, I'm going to get my scope out, haven't used that in a little while, and I'm going to look at these signals and see what's going on with the connections. There's a little bit of disagreement in the documentations about what the hookup is for this thing, and one of them talks about a yellow wire, and then another one not. So I have to assume that the one that speaks of no yellow wire is correct for this encoder. I don't want to damage it, so you got to be careful. So I'll go ahead and get the scope and hook that up, and apply the necessary voltage to this guy and give it a spin, and we'll see what it looks like. Okay, so I've got my experiment set up here so that I can look at the output of the rotary encoder. This is, as I mentioned, it's an incremental encoder, so all we're going to get are pulses. they're using this little developmental board, their tiny developmental board. I've wired up a circuit, and I'll show the circuit up at the top here so you can see how it's wired. But the way it's working right now is that there's a little bit off camera is a DCC supply that normally is used for my Arduino boards. So it has that kind of Arduino connector on it. And then what I did was I kludged up a sort of a connector to tie to the end of the Arduino connector and be able to plug it into the board and supply the necessary voltage for the rotary encoder to work. And it's supposed to take between 5 and 12 volts for the encoder. So I've got it set. This happens to output 9 volts. And so what I want to do with this setup now is I've currently got the meter also connected to the input voltage, so I can verify with the meter that it is in fact a 9-volt signal. And then I've got the scope connected to just one of the A phase of the output of the rotary encoder. And so the A phase will be displayed on the scope. And what I'll go ahead and do with the camera capturing the scope better is I'm going to power everything up, and then I'm going to rotate the encoder. But I'm going to use the single sweep setting on the scope to capture the pulses as they come out. And hopefully then I'll be able to display what it looks like if you have pulses for a clockwise rotation, and then I'll do it a second time and try to show what the pulses look like in a counterclockwise rotation. Okay, so I just did a single sweep with the 2 pulses, and the colors are with the yellow is the A phase and the blue is the B phase. And so where you see the pulses begin is where I started rotation, and you can see that on this case the rising edge of the yellow is leading the rising edge of the blue, so that the A leads the B when I did that was a clockwise rotation. So now let me do a counterclockwise and I'll show you what that looks like. So I have to push the single sweep and oops, triggered the single sweep. It's pretty sensitive. Okay, this is counterclockwise, and now you'll notice that the rising edge of the B blue pulse leads the rising edge of the yellow one. So that shows what the pulses are doing for the quadrature as the incremental encoder is being rotated. By now, I'm sure somebody watching this video is going to say, well, John, all you're getting are a bunch of pulses and you have no idea where the actual rotation is going to. And yeah, that's a fact. What has to be done is what's called a homing strategy. Something has to be added to the system that has a unique position, so that when it reaches that position, it issues a signal, and that the whatever's controlling the rotation then can determine that whatever amount of counts from there constitutes a certain degree of rotation in one direction or another. So I had a couple of ideas about how I want to do a homing strategy, and one of them involved taking on the shaft below the main deck of the turntable. I wanted to cut like a small hole through the shaft, a very small diameter hole, and insert a piece of wire in it so that either end of the wire would be cut flush with the shaft, and then there'd be a brush on either side of that, so that whenever the shaft rotates in contact with the wire inside the shaft, the two brushes would conduct, and some resistor in series would indicate which direction that the bridge is facing. So that's one idea. I mean, there's a lot of ways of doing it that would all equally work, but right now I'm kind of clinging to that one, so we'll see. So yes, I need to find some way to know what the home position is. Well, I have one more concern that I want to share about the turntable project. Pardon me. Oh, great. Perfect timing. I have yet another concern that I want to share about the turntable project. And the bridge has a signal with the DCC on it that it gets from below the bridge. There's two rings, conductive rings, that are separated by a small gap. And then there are two copper, I'm showing it this way, there's two copper brushes, if you will, or contacts that lay up against the rings. So when the bridge rotates, these two rings have a circuit path from the DCC supply, which would be your controller, and these rings, which in turn, each ring has a wire soldered to it that comes up through the base of the bridge, right? There's a little hole there, and then goes up to the track. You solder it to each wire to the track. So now the bridge has its DCC signal. So what my concern is about that is when the bridge is static and you have the rails coming in from the yard up to the rails that are on the bridge, there's a small gap in between to keep them from conducting to one another. And it's small enough where when a train comes in across the rails of the yard, it can roll right up onto the track, provided that the track contacts have the polarities matching what's coming in from the yard. Okay, so as long as they're matching, there's no problem. But if I want to reverse the steam locomotive and I turn the yard, I turn this around, and there's still a gap, so I don't have a short. But as soon as the locomotive begins traveling back across there, it goes across that small gap between the yard and the bridge. It'll be a short because you've reversed the polarity by turning it. And so it needs to be considered as, how do I control this short? How do I get rid of it? Now, on the internet, there you can find a lot of auto reversing modules, at least a number of them, as I said, and they do basically that. They will detect the short and they will reverse the polarity. But I had a thought about it. I've already got, those things are expensive, by the way. I think they run about $50. To me, that's, no small potatoes. So I already looked at a number of different ways that I might combine. I've already got investment in the motor controller. So I've got a micro, and here's my layout on this thing so I can diagram my story. I've got a micro, and this micro it's got some signals going to the motor controller, which in turn is routing the motor voltage to the motor. And under control of the micro, it can start, stop, and reverse, okay? It just changes this is a DC voltage going to the motor here, so it's either on or off, or one polarity or the other. And I can do that with a single chip. And I'll talk more about that motor controller circuit in the next episode when I do the electronics. But since I already have this part of it, I thought I could just add to it. This says, it's hard to read, it says it's a reverse control. And the reverse control is going to have the DCC signal from the supply or the controller going in and then to the track, the same two signals, only they're reversible by this control here. So the same signal coming to the track can be used to detect a short circuit. And so when it detects a short circuit, it'll reverse the polarity under the microcontroller. I'll use an interrupt to the microcontroller that's generated by this reverse control circuitry, and then the micro will immediately set a timer. So this can change. Probably everything in this has to be pretty quick. So the micro has to be fairly fast. The short circuit detection has to be real quick with that interrupt, and then the polarity control circuit, more than likely solid state relays, have to be really quick. So we respond as fast as possible to eliminate that, because whatever short happens here is also seen back at the controller. So the trick is to reverse the polarity and remove the short before the controller says, I'm going to shut down. We'll see how that works. And it really ought to prove to be kind of an interesting exercise. And worst case, if I can't do it, I'll buy an auto-reversing module from the internet. But you see what my plan is and some of my thoughts right now. And so I'll flesh all of that out in the next episode and present some circuits. If it's successful, I'll present some more circuit drawings that will go into more detail about how I hope it will work, and perhaps even run some experiments. But I want to show a picture. I meant to show this picture earlier. There's a picture of the brushes on the two cylinders here, the round contacts, and I'm going to include it. I'll put it in the video right over here. And I want to make sure I mention that. I got that picture off of a video that was done by a fellow whose YouTube channel is called ACHB Railway. And the video was posted back on March 8th of 2024. He does an outstanding job of going through the manner in which this kit has to be or will be built. He also identifies a lot of the problems that are inherent in building this kit. And so it's great to have that resource in an advanced knowledge base so that I can run around the problem, so to speak. But I'll put a link in the description to the fellow's YouTube video. And so if anyone's interested in that, they can go take a look at it. Ed and Mary Ryan have just finished watching this video. And I think we should listen in. There's about to be a little conversation between them about it. Man, that was a good video, Mary. A good video. Well, if you say so, Dad. I do, Mary. Best video ever, girl. That's nice. But I didn't leave a light. I just forgot. Oh my goodness. Poor Mary. She forgot to leave a like. Well, I hope none of you make that mistake.